So depending on the part of the country that you live in, you may have a major problem with capacitor failure or not. And we notice that in hotter states, states with higher temperatures, that we see much higher rates of run capacitor failure. Now, the first thing about this video, if you don't hear anything else, I want you to hear that this is about run capacitors. So capacitors that stay in the circuit all the time. And for the compressor, condenser fan motor, and the blower motor. And a run capacitor doesn't have a relay in it like a start capacitor. And so it's not affected by turning it on and off. It doesn't have to come out of the circuit at a certain point like a start capacitor. So a lot of the confusion that I see when it comes to things that technicians think of as causes for failure, those are causes for failure for start capacitors, but not for run capacitors. So the reason for this video is when you have something that fails as much as run capacitors do, especially in certain parts of the country, people want to come up with theories about why they fail. And it's important that we know what can cause them to fail so that way we can do what we can to prevent it, and also so that we don't tell people the wrong thing. We don't want to tell people that something causes something to fail if it actually doesn't cause it to fail. So in this video, we explore some of the different common theories out there. And so some of the common theories are that if your motor is drawing high amperage, that will cause the capacitor to fail sooner, so that there's something that goes on inside the motor itself that causes the capacitor to fail. Many have said that they notice that a system that's low on charge seems to have weak capacitors, or a system with a dirty condenser coil seems to have more commonly failed capacitors. Some people have said, including my own brother, have said that they've noticed that it seems like capacitors fail more often when the voltage is low, the applied voltage coming in is low. And so I want to explore this. And to start with, before we go any further, you have to have a basic understanding of what a capacitor is. And the best way that I can kind of get you to imagine it is think of a capacitor, a run capacitor, like a storage tank or like a pressure tank. So if you're used to pressure tanks in, say, a well pump, for example, you understand that it pressurizes that pressure tank, and the amount of water that can be stored in that pressure tank is contingent on the incoming pressure. So you can't have more pressure in the pressure tank than the incoming pressure coming in. And that's how a capacitor works. A capacitor can store the electrons that are forced into it, but at some point it can't store anymore, and that's dictated by the amount of pressure, which is why the amperage of a capacitor is dictated by the voltage applied to it, the capacitance of the capacitor, and the frequency. And so first off the bat, if you're in the U.S., the frequency is pretty much 60 hertz. Now, could there be some cases, we see capacitors installed in variable frequency drives and whatever, where you have some various frequencies, and so could that affect the capacitor? Absolutely, it could. But for most of what we do, it's pegged at 60 hertz, and in Europe and other places, it's at 50 hertz. So if your hertz stays the same, your frequency stays the same, and your capacitor has a certain capacitance rating, then the amount of electrons that can go in and out of that capacitor are now just fluctuate based on the voltage. If you think of it like that pressure tank for the pump, it can receive electrons and it can store them, and then it can release them. That's essentially how it works. And as that phase changes, it's constantly storing and releasing 60 times per second. So we're going to explore some of these things and see if we can test and prove exactly how this works, give you a better sense of what can actually cause a capacitor to fail. The question is, what are the things that can cause a capacitor to fail? And there's a common belief in the field that there's something that the compressor can do or the system can do to cause the capacitor to fail. But the more that I research it, the more we learn that the capacitor has a fixed amount of current that can go in and out of it. And so I want to do some demonstrations here to kind of show what I'm talking about. First, measure the voltage and then the amperage off of this. So I've got the Testo 770-3. So we've got 291 volts, and we've got, into our start winding, we've got 4.2 amps. Okay, so we kind of have that as our baseline. 4.2 amps, 291 volts. So we've got 212, 213 volts, something like that. just an image of a typical capacitor. And then over here, we have a kind of an old school wiring diagram. And so what we're going to be focusing on is the capacitor. That's this part here. And then this is a dual cap. And a dual cap, one side would be the C side. And so the C side would be the side that connects over to the run side of the circuit. So one of the legs of power. The same side of the leg of power that connects to the run side of the circuit is the one that goes to the C terminal. And then our herm side is the side that goes over to the start winding. So let's establish some things here. In order for you to have a potential difference, a difference of voltage between C and S on the start winding, see here, we have to have a movement of electrons in and out of this capacitor. So a couple quick rules here. Capacitor electrons cannot pass through a capacitor. They don't go through one side to the other. They can't. There's no connection between the C and herm sides inside that capacitor. There's just an attraction across the plates. So they gather on one side. So, positive charge gathers on one side and negative charge on the other. And then as the phase switches of the incoming alternating current on our lines, then it switches back. And so what this capacitor does is it adds in a phase shift. So it adds in a 90-degree phase shift, which helps correct for the phase shift that occurs in the inductance of the motor. A motor is an inductive load, and so there's this thing called inductive reactance. We won't go into that, but it's correcting for, it's creating a unitary power factor, and it's helping the motor run in the right direction with torque. We'll keep it really simple here. When you have a run capacitor, that capacitor has a capacitance rating. So this capacitor here, we'll say it's a 45 by 5. But in this case of the compressor, it has 45 microfarads. Microfarads describes how many electrons can be stored and discharged in and out of that capacitor. So the only electrons that can go through this start winding are ones that can store in the other side and then back again. Now, that can change with frequency, but as you know, with a typical compressor capacitor, your frequency doesn't change. And since the frequency stays at 60 hertz, then the amount of current that can go in and out of this capacitor are completely dictated by the capacitor itself. Now, capacitors have voltage ratings on them. We've talked about that. And so if the voltage goes higher than what the capacitor is rated for, then the capacitor can fail because the electrons can actually bridge either across the two plates or it could bridge to ground, and that's a problem. Another thing we know is that the changes in ambient temperature can also affect the life of the capacitor. All right, so we've got a 90-degree ambient condition, so it's good and warm outside. I'm going to use this K-type bead probe and attach it to the capacitor and see what we're reading with it running normally. I've got the bead probe attached to the K-type. I've got the K-type thermocouple attached, and it's running 91.6 degrees right now. So just barely over ambient temperature, which is good. It's been running for quite a while now. I've set the temperature down so it'll keep running. I have it connected with alligator clips. I'm measuring the wattage and the power factor, and it's showing that I'm at unity power factor, which means that capacitance is doing its job to overcome the inductance. That's a whole nother kind of conversation, but I just wanted to make sure that the capacitor is indeed functioning properly, and definitely is. So everything's sized properly. So now let's see if we can get the temperature to go up on this capacitor by short cycling the equipment. All right, here we go. Don't try this at home. This is not good for the unit. I'm going to short cycle it like crazy. Interesting kind of unintended consequence happened here. That compressor is running backwards by the sounds of it. Yeah, we got a backwards running compressor now. So I'm gonna let it reset enough that it can actually run properly, so I don't damage it. Yeah, so this is a pretty new unit, and it was only installed 3 months ago, and it's got a Copeland scroll in it, so it's a good compressor. But yeah, we definitely saw that short cycling caused it to run backwards, which, when that happens in real life, that's not a good thing. It's not going to run properly. We were only drawing 3.6 amps on common wire, Whereas before we were drawing over 7 and you could hear that sound. It was just definitely not right. Now we're back running normally again. You can see so far, no change. So first off, you can see on this graph, it shows you that the higher the voltage is, anything above the rated voltage, it very quickly decreases the life of the capacitor. So if you have a high voltage surge from the power company, or you have a lightning strike or anything like that in the area, then that's going to greatly decrease the life of the capacitor. You're going to get bridging across those plates, and it could very easily cause it to fail. And then if you look at this next image here, the higher the temperature is, the shorter the life of the capacitor is going to be. The lower the temperature is, the longer the life of the capacitor is going to be, the ambient temperature around. What you're not going to see is an amperage rating. Well, why is that? Well, because amperage current is dictated by the number of electrons moving through a conductor, and that number through the start winding is completely dictated by the capacitance. Now, some of you may say, hey, I know for a fact that I see high current on a compressor when it starts up. So I think a locked compressor can cause a capacitor to fail. I think high current can cause the capacitor to fail. So you're reading on the common lead, the lead coming from the common terminal. Now, common isn't a winding. It's just a point in between run and start. So when you read current on common, what are you reading? You're reading run and you're reading start. You're reading the current on both of those lines, right? If you were to just measure on the start winding, though, do it sometime. If your meter has an inrush feature on it, put it in inrush mode and measure your start amps. And you'll notice that your start amps with a normal system that only has a running capacitor and not starting capacitor or starting capacitors, it will not draw high current. You will notice that when you have a start capacitor in place and a potential relay, that initially when it starts up, you will have high current on the start winding. That's expected because the start capacitor only stays in the circuit in the start winding for the first couple milliseconds until that compressor gets up to 80% of its total speed. So that's going to happen very, very quickly in the first fractions of a second. If you have a meter that can do this, that can read that inrush amps, then you will see a higher start reading when it starts up, and that's only because you have the additional electron capacity of these capacitors in the circuit. If you don't have this whole setup in here, you don't have a start capacitor with a potential relay, and you only have a run capacitor, then your amperage on start and run are going to be the same because your amperage are dictated by the number of electrons that run capacitor can hold. Experiment sometime. Put in a smaller run capacitor, smaller than it's rated for, and measure your start winding amps. Then put in a larger run capacitor and then measure your start winding amps. You'll notice that when you put in a larger capacitor, you have more amperage. When you put in a smaller capacitor, you have lower amperage. So the amperage of your start winding are completely dictated by the voltage and by the capacitance. Now, some people will point out, well, your motor does add inductive reactance. When you measure in between these 2 points, between start and common, you see a much higher voltage than the applied line voltage. And that's because of the back EMF that occurs within the start winding. It's back electromotive force. Your motor actually acts like a generator as well and actually generates a higher voltage. But again, the highest voltage that your motor is going to generate is when it's up to full speed. That's not going to be during starting. And much of the things that are attributed to failures in a capacitor are when people say, well, when the motor has a hard time starting or when the system's short cycling, then that causes your running capacitor to fail. Now, high ambient temperatures can cause your running capacitor to fail. So if the unit's getting hot, you have a failed condensing fan motor or something like that, then that can cause it to fail prematurely. And then also high voltage conditions can cause it to fail prematurely. Or if you had some, higher frequency or something, that could cause it. That would be extremely abnormal. But with all things being usual, the only things that can cause a run capacitor to fail are high voltage, high current, or a run capacitor that is poorly designed, poorly executed, poorly manufactured, or it's just at the end of its life. So everything has a life expectancy over time, but that's the reason why I am a big fan of the AMRAD capacitors, because we've seen that they perform more to spec than some of the other ones that we've seen. We see that they're very well made capacitors. So that's it. What can cause a run capacitor to fail? Well, the only thing that can cause it to fail is higher voltage, which also could lead to higher. If you have higher voltage, then you will have higher amperage on your start winding. Higher than designed voltage or higher than design temperature, or just higher ambient temperatures over a longer period of time will also cause failure. All right, so let's try it again. I'm going to try to give it a little more time in between my short cyclings. Now we're going to test inrush amps on the start winding and show the difference between inrush and full load amps on the start winding versus the run winding. All right, so this is our regular running amps on our start winding coming from our capacitor, so that's connected to herm. Normally it'd be connected to herm. This is a AMRAD Turbo 200, so it's connected to 45 microfarads. I'm going to go ahead and shut it off, and then I'm going to put it on inrush amps. All right, there we go, inrush amps. So now let's see what we get on startup. Let's try it again just to see if there was something weird going on there. Amps, it's currently off. Inrush, there we go, inrush amps. Let's see what we get. Nothing. All right, now we're gonna try it again on the common of the compressor. Actually, let's do it on run, just so that because what I'm wanting to show you is that it's run that sees that inrush not start. Okay, let's hit inrush. So this is on the run winding of the compressor. Here we go. All right, so there we had an inrush of 60. We saw no inrush on start at all, didn't even log it. And that's because on the start winding, the capacitor inhibits the amount of current that can flow through. The amount of current that can go through the start winding is completely dictated by that capacitor, because electrons aren't allowed to move actually through the capacitor. They can only go in and out of the capacitor. So the capacitance dictates that. You can see here, still at 92 degrees, even after all this monkeying around and short cycling that I'm doing. What you see on common is start plus run, right? So you get that. So let's now measure the inrush amps on common to help additionally prove that all of the inrush is on run and not on the start winding. Inrush, there we go. All right, now. Well, would you look at that? Common and run show the same inrush, and start doesn't show an inrush at all. So if we have a locked compressor, that capacitor is not going to see that increase in amperage. That increase in amperage is going to be seen on the run, not on the start. In some cases, you're going to notice that your run wire is connected not back to the contactor, but actually back to the capacitor. So in some cases, your run winding isn't going to go to the contactor, it's going to go to the capacitor, and then the capacitor acts as the junction point. In that case, you will get additional heat because it's using the capacitor as a connection point to make connection for run. In this application here, your run winding goes right back to the compressor, goes right back from the contactor to the compressor, so any heat that's built up is going to be built up through here. It's not going to go to the capacitor at all. If you look here, we've been messing around with this thing for a while now, and our temperature of our capacitor is not increasing. When we talk about amperage, we're always talking about amperage on common. That's where we measure it. And so the assumption that a lot of technicians have is that when you see an increase in amperage on common, that's going to equal an increase in amperage on start. But the thing that they miss is that the amperage on start is dictated by the capacitance of the capacitor and the incoming voltage. Higher voltage is going to result in higher amperage on the capacitor, and the capacitance of the capacitor is going to result in higher amperage on the start winding of the capacitor. Some techs get confused. They combine together the concept of a start capacitor, which has very high capacitance and thus will have a lot of amperage on it, but it's supposed to be taken out for a short time, with a run capacitor that is always in the circuit. A run capacitor never comes out of the circuit. All right, so this may be another way that's kind of helpful to you to understand what I'm talking about, because the thing that techs have a hard time getting their head around is the fact that the capacitor is what dictates the amperage on the start winding. It just doesn't seem right, because we just imagine that somehow electrons are coming through one side, getting boosted up, and then going to the compressor. Like, that's how a lot of techs imagine this, and you got to get your head around the fact that that's not how it works at all in order to help this make sense. What's actually happening is you have a current that's going to travel through here and then go to start. This is common. And then it's going to go through to start, store, and then release back the same direction that it came from. And that's what creates that phase shift. And then we also have a higher voltage applied on it because of the back EMF from the motor. And so in this example, this is how to test a run capacitor under load. It's on the resources tab of hvacrschool.com. And so here you can see we have an applied voltage across the capacitor of 292.9 from here to here. And then we have a compressor start wire 7.8. This is actually a real unit I got these readings off of. And so if we want to find the capacitance, we can use these live readings, right? Well, how would that work if this amperage wasn't completely dictated by the capacitor and the capacitor size, and the voltage. You understand that it wouldn't work. The amperage, the voltage equal the capacitance, and that's how we do it. So we take the amperage, 7.8 amps, we multiply it times a constant, 2652. Some people use 2653 or 2650, makes very little difference. 7.8 times 2652 divided by the applied voltage equals the capacitance. You'll notice it doesn't, nowhere on here are you taking the amperage of the compressor other than the start wire. You're not taking the run wire amperage. You're not taking the common wire amperage. You're not measuring the applied voltage or any of that stuff. You're literally just saying, what is the voltage applied to the capacitor? And once you know the voltage applied to the capacitor and the amperage, then you can determine the microfarads of that capacitor under load, which indicates to you that it's the capacitance and the voltage that dictates the amperage that the compressor is going to draw on the start winding. The only way that you could have higher amperage on this start winding is if you had higher voltage or higher capacitance. And the voltage increases above the applied line voltage based on the back EMF that comes from the motor, which only happens when the motor starts to speed up. So that tells you that if anything, when you only have a run capacitor in the circuit, that if anything, your amperage will be lower on your start winding when it starts than once it starts running, because that back EMF only comes up. This voltage only increases once this motor gets up to speed. All right, so let's do another quick demonstration. So a lot of technicians, you know that this is a run capacitor, right? Something real quick, there's no relay in this. This is constantly in the circuit when it has voltage applied to it, when it has potential applied to it. A lot of confusion between a start capacitor, which has a potential relay that takes it out of the circuit, and a run capacitor, which constantly stays in series with the start winding of a motor, okay? So this stays in the circuit all the time. But let me ask you a question. If I take this plug and I plug this into 120 volt source and I connect it to this capacitor, what's going to happen? Well, some guys think, I've asked a few, and some think it'll do nothing. Some think that it will be a direct short. And so let's show exactly what happens when you connect it in that way. So this is a Turbo 200 mini IM, and so it has a 5, a 2.5, and a 7.5. So we're going to go for the 7.5. We're going to go for the gusto here. 7.5 is the brown, and then we're going to connect this to the center. I'm going to put on my gloves, my glasses, so that way I don't hear it. Remember what you think is going to happen first, and then I'll show you what does actually happen. And rather than showing you the voltage, I'm just going to prove it to you by showing you the amperage on this wire. Look at there. Thing's drawing half an amp. Drawing half an amp? How's it drawing half an amp? Is it actually creating any heat? Is it doing any work? The answer is no, it's not. That is all reactive power, which means that it's creating an out of phase, so it's storing and discharging. It's taking from where it came from and then putting it right back again. That's what a capacitor does. If you imagine it almost like a balloon, fills up and then discharges, fills up and then discharges. That's sort of what it's like. But there's no actual connection in between these terminals. These two terminals aren't shorted together. You have a plate and then you have a magnetic field or an electrical field that builds up on either side of the plates that attracts and then repels the electrons in and out. So this thing is like a little electron balloon that's just constantly filling up and discharging, filling up and discharging. And there's a differential charge across those two terminals. What will happen if I apply a higher voltage to this? Well, first, before we do anything else, I want to show the temperature of this capacitor with it unplugged and then with it plugged in. So you can see we're unplugged here. I'm going to go ahead and discharge the end of this because right now there's actually a charge here. Again, this is the correct way to discharge your capacitor with the discharge, which is a 20,000 K 10 watt resistor that I have connected in there. All right, so let's measure the temperature. So first, let's take a look at the ambient right now. Well, the ambient temperature actually went up quite a bit. We're at 95 degrees right now outside. So we're going to use this K-type bead probe. All right, the actual temperature of that metal is below the outer ambient because I just brought it in from outside. So we'll let that stabilize for a second, see what we end up at. Now, one thing to know about these is these are rated at over 150 degrees Fahrenheit. So regular ambient conditions shouldn't cause these to fail. But what we do know is that increases on ambient conditions can cause them to fail earlier than they would otherwise. So it's not like being in a hot temperature environment is going to make it fail. But what will happen is if you're in a higher temperature ambient environment, it's not going to last as long. All right, so we've stabilized here at 86.9. Now let's go ahead and plug it in. So we're going to have some current passing in and out of it. So you actually now have electrons going in and out of this capacitor. You can prove it. There you go. Got electrons going in and out of this capacitor. Now the reason why these capacitors have metal shells, they have oil inside of them, and that oil helps keep them cool as those electrons are passing in and out. Because there is some heat generated as those electrons are moving in and out of the capacitor, and because it's always in the circuit, it never comes out, it doesn't have a relay that takes it out, it needs to have something to keep it cool. Now over time it will slowly increase in temperature, but with the oil fill and the amount of load that I'm applying on it right now, it's not going to increase any significant amount. I've actually tested some of these before. Obviously it's going to increase in temperature because the outside is warmer than 87. So now let's go ahead and apply a higher voltage to it. I have it connected to a disconnect. It's actually 208, so it's going to be about 213 volts, 213 volts. Right now, our temperature's been rising because it's hot outside, so right now it's 88.7 degrees. It's kind of hard to see with the glare, but 88.9 degrees. Let's see if that temperature keeps increasing. All right, so now we're going to check the amperage. You can see the amperage went up with the voltage. So as the voltage goes up, so does the amperage. Now I'm going to show you the voltage that we're seeing on it. You'll notice that the temperature is not really going up, just the capacitor doing its job. .213 volts applied across it, 60 hertz. The capacitor's not heating up, it's just got power going in and out of it, because that's how a capacitor works. It wouldn't really matter if I connected a motor to it or not. That's not going to change what it does other than the voltage, the back EMF being applied from the motor. So if you measure that applied voltage across those terminals and you know the capacitance of the capacitor, then you're going to essentially know the amperage. You know what it's going to be. If you think about the capacitor equation that we use for calculating capacitance, it's you take the amperage, right, of the start winding, you multiply it by 2652, and then you divide it by the voltage, and it gives you the capacitance of that capacitor. It's in a 60 hertz application. And so if you work that math any other way, you can see that if the capacitance is known, if you already know what the capacitance of the capacitor is, and you know the voltage, then you already know what the amperage will be. What that tells you is that starting up a motor, or basically anything that motor does, that's not going to affect the number of electrons that capacitor can hold. The only thing that will affect it is the voltage. And so as a motor ramps up, that's when the back EMF comes into play. That's when you get that back electromotive force. You don't see that back electromotive force until the motor starts to speed up. And so a motor that's short cycling or that's having a hard time starting is not going to cause a capacitor to have more current. And without that, how could the capacitor heat up? The only thing that can cause the capacitor to heat up are external conditions, like if you have a run terminal that's also connected on the C terminal of your capacitor, and then that's a point of heat, or if it's in a hot environment to begin with. For example, if you have a condenser fan motor that's failing, and because of that your entire condenser is running hot, well then your capacitor is going to run hot too, because of the increased ambient conditions, increased temperature around the capacitor. So what we know is increases in voltage cause capacitors to fail prematurely, and increases in ambient temperature cause capacitors to fail prematurely. So the cooler you can keep the capacitor, and the more you can keep the voltage near its rating, or obviously below its rating, then the better it's going to last. If you get that voltage above its rating, then you're going to start getting bridging. It's going to actually, some of the electrons are going to start to bridge, and they're going to start to damage the internals of the capacitor. All right, so hopefully you found that helpful. A couple things that I want you to know about these run capacitors and how they're tested. They're tested to last for 60,000 running hours. It's not cycles, because in a run capacitor, they're in all the time. There are no real cycles. The unit goes on and off, but you're cycling 60 times per second anyway. Your voltage, your sine wave is going up and down 60 times per second anyway, so turning it on and off isn't the issue. It's how many running hours does it run. And 60,000 hours is a long time. It's somewhere between 10 and 20 years, depending on what part of the country you're in. It's a long time of running a typical air conditioner. And they're tested so that they should work fine up to 70 degrees Celsius for 60,000 hours, not 70 degrees Fahrenheit, so that's 158 degrees Fahrenheit. Case in point, under normal operating conditions, capacitors should last a really long time if they're keeping their manufacturer rating, if they're actually tested properly and made properly, based on there's several different standards, but that's the old U.S. Tecumseh standard is the 60,000 hours at 70 degrees Celsius. So there's 4 things that I've identified that can cause run capacitors to fail. The number 1 most common is overvoltage, and we call these transients. That would be power surges. A lot of them are caused by lightning down the line from the power company. The best way to help reduce transients, the best one that exists right now, is using a good quality surge suppressor. Using not a cheapy one, a good quality surge suppressor is the best way to help prevent those problems with your capacitors, because those are going to help kind of take those voltage transients and shunt them to ground before it gets to your capacitor. And again, in theory, and it depends on there's a lot of different factors when it comes to these surge suppressors of whether or not they're going to be effective in actually doing that. But even small spikes in voltage can cause a run capacitor to fail, especially as they accumulate over time. Because run capacitors, they fail, small little sections get burned out, and then eventually you'll have massive failure. So when you see a run capacitor where it's getting really weak, that's what's happened, is that segments of that foil on the inside, segments of that metal coating have melted off. And so you reduce the capacitance over time, and you'll see that quite often. But the term for the type of surge suppressor that I recommend is a thermally protected metal oxide varistor. Are there better ones out there than that? There are some industrial grade surge suppressors that are going to do a little better, but a thermally protected metal oxide varistor surge suppressor installed properly with a very short ground on it is the best bet that you're going to have to protect against these over voltage conditions that are coming down the line. Now, some people have asked, can the back EMF from the motor be too high, and can that cause it? Now, the answer to that is not really. I mean, you could have a motor that produces slightly more back EMF because it's running at really high speed. An example would be you have a motor like a compressor that's under really low load, and so it's spinning faster, and so it's generating a little bit more back EMF, but that still shouldn't be enough to take it over the voltage rating of that capacitor. Most capacitors we work with in the air conditioning side are 370 or 440 volt ratings. It's going to be pretty rare that you have a voltage failure because of back EMF coming from the motor. Because again, a motor being under greater load that causes it to run slower will result in less back EMF, not more. It's kind of nerdy stuff, but some people have asked that question. Really what it comes down to is the applied voltage down the line, getting transients, getting voltage spikes down the line, and reducing that will help increase the life of a capacitor. The next thing is the temperature of the capacitor. Now, like we mentioned here, the lower the voltage is applied to the capacitor, the longer it will last. Even when that voltage is decreased below its rating, the further below the rating you are, the longer the capacitor will last, which is why 440 volt capacitors last longer than 370 volt capacitors, even if the applied voltage never gets close to 370. The same thing is true with the temperature. The cooler you keep a capacitor, the longer it's going to last. Now, some people have mentioned that some capacitors are mounted in the airstream, and so when that airstream is higher temperature, it's going to increase the odds that that capacitor fails. The temperature of a capacitor can increase because of all the different types of heat. You could have conduction, you could have radiation, you could have convection. All of those things can transfer heat to that capacitor. And so when you have a capacitor that's in the condenser airstream, or it's exposed to the condenser, if you have a really high condenser temperature because of a dirty condenser, that could increase the temperature of that capacitor. And again, anything that increases the temperature of the capacitor will reduce its life. That doesn't mean that it will necessarily make it instantaneously fail, because again, they're designed for 158 degrees Fahrenheit. It's unlikely that you're going to get into that range, but it's something for you to at least think about, that is possible. And if you think about some things like a heat pump, for example, with a blower capacitor inside the heat pump that's mounted next to the blower, you will have cases where that air can start to approach that temperature. Anytime you have higher temperature ambient conditions that capacitor is exposed to, whether it's through radiation or conduction or convection, then that capacitor life is going to be decreased. So we've got over voltage, we've got over temperature. High ambient temperature can cause it. We have installation considerations. And so you want to install most capacitors upright. And the reason is because there's a little bit of a void inside that capacitor where there's no oil. And if you flip it upside down, part of the capacitor windings can be exposed to that void, versus when you have it right side up, only the terminals are exposed to that void. Now, it depends on the capacitor manufacturer, whether or not that's the case. A lot of people have mentioned that a lot of manufacturers place them sideways or upside down. I'm not going to pass judgment on that. I'm just telling you that it's a known best practice to mount capacitors right side up. Another thing is how tight the terminals are on the capacitor. So the terminals need to be snug on the capacitor. The other thing is if your run winding is using the capacitor as a junction point to get back to the contactor. That's also a point that can cause that capacitor to get hot especially if you're having issues with the compressor. So if the compressor is short cycling or something like that, and you're using the capacitor as a junction point, as like that, it's connecting to that C terminal and then back to the contactor, then that can also result in high temperature of the capacitor because that terminal is going to get hot. So you want to make sure it's mounted right side up in most cases. You want to make sure your connections are really tight. And when possible, bring your run winding connection, your run winding wire right back to the contactor versus taking it to the capacitor and using the capacitor as a junction point. And then as it relates to all the other system conditions that could potentially cause it, I can't see any reason why undervoltage can cause it. I can't see any reason why all these other system conditions can cause it, other than if those system conditions make the condenser a higher temperature, which then causes the capacitor to be a higher temperature. Like I said, we've done a lot of testing on this. Hopefully that's helpful to you, gives you some things to look for and maybe some things to do about helping to prevent capacitor failure. But the biggest thing you can do is use a high-quality capacitor. That's why we use AMRAD and the Turbo 200. It's American-made, and they do a really nice job testing it. All right, thanks for watching. We'll see you next time.